number 3, so if you consider one, that is this one, so if you consider a double cone S x y z belongs to R3 such that x square plus y square equal to z square. Okay, but this does not represent a surface, doesn't represent a surface. Why? Because if not,
ডবল ডবল করে মিড পোর্শনটা কি প্রবলেম করবে?
প্রবলেম করবে, তাই না? এখানেই সমস্যা হয়ে যাবে। কারণ তুমি if not, let us suppose that sigma colon u to s intersection w be a surface patch containing 0 0 0, right? Okay, 0 0 0, and let sigma of small a equals to this, as it is a homeomorphism, so it is in particular onto. Okay, so we may consider u to be an open ball centered at A. Okay, and note that the open set W, so it will must contain a point P in the upper half portion of the double cone of S, where z greater than 0, and a point Q in the lower half portion part of S, where z less than 0. Okay, and for these 2 points P and Q, you are going to have 2 points in U. So let B, C be the corresponding points in U with respect to P, Q respectively. Okay, respectively. Okay, okay. Now, so that means so you are in R2, and suppose this is your open ball, this is A, this is U, and this is B, this is suppose C. So since U itself is path connected, so you are going to have a path uh, yes, this way, missing the point A. Okay, so you are going to define, so we can define a curve or path, whatever you are, in U passing through B and C, but not passing through A. Okay, now if you impose this sigma on this path, this is your alpha. So if you impose sigma on this path, if you restrict your map to this path alpha, to this curve alpha, then what you will see, so then this alpha will be mapped to alpha cap, which is sigma compose alpha, right? Okay, which is sigma compose alpha passing through alpha in S. Since alpha is a homeomorphism, sorry, since sigma is a homeomorphism from U to S intersection W, and if you restrict sigma to alpha, then that curve is in S, passing through so sigma of B is P and Q respectively. But since the curve alpha misses the point A, so the image of this curve with respect to under sigma, it will miss the point 0, 0, 0 respectively, which misses the point 0, 0, 0, which is impossible, right? Because if you just you draw this double cone again, so this is your Q, this is your P, so it will miss, yes, and this is your 0, 0, 0, so this is your P and this is your Q and this is alpha cap. Okay, which is not possible because you are assuming that sigma is a surface patch, so the image will be content in the double cone intersection W. Okay, so this contradiction leads to the conclusion that this contradiction So this contradiction uh, will lead to the conclusion that the double cone S doesn't represent a surface. Okay, doesn't represent a surface. Okay. Now, if you come to another, uh, if you come to the surface S2 again, the set S2 again, you will see that so if we consider S2 again, then we see that then we see that there may be maybe other atlases of S2, one of which will be defined as follows. And which is different from the previous two surface patches, previous two atlases of S2. So this can be represented as sigma x plus minus. So it will be the set of all those points like that, 1 minus y square minus z square y comma z, where y square plus z square is less than 1, sigma y plus minus, so it is plus minus sorry, it is x comma plus minus root over x square 1 minus x square minus z square z, where x square plus z square less than 1, sigma z plus minus and it is x y root over plus minus 1 minus x square minus y square, where x square plus y square less than 1. Okay. So yes, so there are so the atlas contains 6 surface patches, right? So they are actually okay. So it will be your sphere, yeah, and you are going to define and just writing down this one. this one, and if you go up, then this is yeah. So these are all 6 surface patches. Okay, and and these 6 surface patches will, uh, if you take them together, then it will constitute the surface S2. Okay. Okay. So now it's time to, it is the right time to introduce regular surface in R3. Regular surface in R3. In differential geometry, uh, we need to have a platform. So why one does need regular surface? Because to speak of differentiability on surfaces, right? So in differential geometry, we need to have a platform where we can define a function on a surface to be differentiable, right? And to consider this notion of differentiability, so you need to impose extra structure on a surface, right? So which needs some extra structure, right? So informally speaking, a regular surface, so informally speaking, a regular surface can be regarded as a regular surface in R3 can be viewed as can be viewed uh, as uh, you can view this as, yes, just take pieces of plane, okay, as as a collection of pieces of planes. Okay, deforming them, and by pieces of planes, by yes, by deforming them and arrange them in such a way so that uh, we can talk of differentiability. Yeah, that means since we are looking for differentiability, so that means it does not include edges, self intersections, or sharp points, right? Some peak points, so where differentiability doesn't make sense. Yeah. So yes, pieces, just deforming them, yes, and arranging them in such a way that does not include sharp points, self intersections, edges, etc. Yes, self intersections, and which leads to a place, favorable situation to define, to make sense, to talk of a tangent plane. Tangent plane at points of the concerned space. Okay. So for that reason, we need to consider this type of basic notions. Okay. So now, yes. Okay. So how one does define regular surface? So the definition will be, so first we start from a surface patch and then extend it to any surface. So a surface patch x colon, a surface patch sigma colon u subset of R2 to R3 is defined to be a surface patch regular surface patch if uh, if number one, sigma is differentiable, on U, that is the components of sigma have continuous partial derivatives of all orders on U. This is the first condition. Secondly, sigma uh, so secondly, yes, for each point P belongs to U, the differential d sigma e from R2 to R3 is 1 1, right? So sigma is such that it is said to be regular if for each p the differential d sigma p colon R2 to R3 is 1 1. So a surface patch sigma is defined to be a regular surface patch if firstly sigma is differentiable, that is the components of sigma have continuous partial derivatives of all orders on u. And the second condition is that for each p belongs to u, the differential d sigma p colon R2 to R3 is going to be 1 1. And this condition is the regularity condition, right? And with respect to this condition, you can always have the important effect of inverse function theorem, right? Because d sigma p is 1 1. Okay. So being a linear map, it must be onto. So it is an isomorphism, right? Okay. Fine. Now a surface uh, a surface S of R3 is defined to be a regular surface is defined to be a regular surface if if there exists an atlas of S, if there exists an atlas of S which constitutes regular surface patches. Okay, which constitutes regular surface patches, or you can say that, or if for every point, for every point P belongs to S, for every point P belongs to S, you can find out there exists a neighborhood V in R3 V in R3 and a surface patch sigma colon u to V intersection S of an open set U of R2 such that sigma is a regular surface patch. Okay. So for each point, so for each point, you are going to have a neighborhood V in R3 and a surface patch sigma from U to V intersection S of an open set U such that uh, sigma is a regular surface patch. Okay. The neighborhood, the neighborhood V intersection S is called a coordinate neighborhood. Okay. At P in S. Okay. Now we see that the condition 2, what does it tell you? That for each P belongs to U, the differential is 1 1. So what does it tell you? Is the following. So let us have a look on the familiar form of condition 2. Condition 2. What is that? To make it precise, let us consider standard basis in R2 and R3. Okay. Okay. So let sigma colon U subset of R2 to R3 be a surface patch, be a be a regular surface patch. Okay. Be a regular surface patch. Okay. Now write sigma uh, in terms of components as follows. That is sigma of UV equals to sigma 1 UV, sigma 2 UV, sigma 3 UV for all U comma V belongs to capital U. Okay. Now let Q be a point U naught V naught belongs to U. Okay. 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 Then let us fix V equal to V naught. Okay. And with respect to this assumption, uh, we see that we see that the tangent vector to the curve u goes to u comma v naught. Okay. What is the tangent vector to this curve? U to u comma v naught. What is the tangent vector? Is u1, that is 1 comma 0, right? Just taking the differentiation with respect to u. Okay. This is u1. Okay. The image of this curve under sigma is the curve. What is the curve of sigma? Image of this curve under sigma. So if you let it be alpha, then the image under sigma will be sigma compose alpha, right? So that means is a curve u goes to sigma 1 u comma v naught, sigma 2 u comma v naught, sigma 3 u comma v naught, right? And this image curve is the curve this which will lie on the image of the surface patch sigma. That is on sigma u, right? On sigma u, and has at sigma the point is q, because we have assumed that q is the point in u. So sigma q, at sigma q, the tangent vector, what is the tangent vector? Is, you have seen that yes. What is the tangent vector? The tangent vector is d sigma q u1, right? With respect to the definition of the differential d sigma q from R2 to R3, because it will map the tangent vector at q of this curve to the tangent vector at sigma q, which is d sigma q u1. And what is that? What is your d sigma q? what will be your d sigma q? The d sigma q is the matrix which is del sigma 1 uh, del u, del sigma 1 del v, del sigma 2 del u, del sigma 2 del v, and it is del sigma 3 del u, del sigma 3 del v of u1. That means 1 comma 0. What is that? What is that? Del sigma 1 del u, del sigma 2 del u, right? Del sigma 3 del u, right? 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 At this is at q, that is u naught v naught, and this is at q, u naught v naught, right? So that means it is del sigma del u. Am I correct? Right? In a similar manner, if you take so uh, similarly, if you consider the curve u equal to u naught, right? Then you will see that see that you will see that uh, the tangent vector the tangent vector uh, the tangent vector at yes the tangent vector at sigma q of the image of the curve v goes to u naught comma v is right dx d sigma q e2, and that will be del sigma del v, that is del sigma 1 del v, del sigma 2 del v, del sigma 3 del v. Okay, fine. So now, so with respect to this one, so these the curves u equal to u naught, v equal to v naught, and these are called coordinate curves. Okay, coordinate curves in R2. coordinate curves in R2. Okay. 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 So the condition 2 of regularity of the surface patch sigma, what does it tell you? Uh, Tells you that the matrix of d sigma q the matrix of d sigma q has linearly independent column vectors, right? And what are the column vectors? Linearly independent column vectors. That means that means the vectors del sigma del u, del sigma del v are linearly independent. Or equivalently, if del sigma del u cross product del sigma del v is a non-zero vector. Okay. Or equivalently, you can say that, or equivalently, one of the minors of order 2 of the matrix d sigma q, it is different from 0, right? One of the minors of order 2 of the matrix this is different from 0 at the point q. That is one of the Jacobian determinant. One of the Jacobian determinants, that is del xy, sorry, del sigma 1 sigma 2 del uv del sigma 2 sigma 3 del uv or del sigma 3 sigma 1 sigma 3 del uv be different from 0 at q. Okay. Okay. So that means, so if you draw the picture, so it looks like, so this is your 0, this is your u, this is your v, and if you have this, yes, this is your u. So now if you take q as a point, and then let it be v equal to v naught, and along this direction you consider u1, and let it be u equal to u naught, and along this direction you consider e2. Okay, then with respect to this linear map d sigma q, so how does it look like? So this is your surface patch sigma, it is actually sigma u, right? So that means this is your sigma q, and at sigma q, so the vectors, this is your del sigma del u, and this is your del sigma del v. Okay, okay. So and these are your coordinate curves, you can make them precise. This, these are coordinate curves. Okay, this is the surface patch, and with respect to, yes, these are three. So this is your f1, f2, f3 standard basis. Okay, so regularity means, so at each point these two vectors are linearly independent. Okay, okay. So I should stop here.